Welcome back to one of my lessons, grade 11s. This lesson will cover the basics on electric circuits. Before we carry on with the next lesson, that would be discussing series and parallel resistors in circuits. Right. So in this topic, I want to familiarize you with some basic concepts. And one of the concepts is that of electric current. When you have an electric current, you have a flow of charge. And the flow of charge could be a flow of electrons. For example, in metals, you have the charge carriers are electrons. In electrolytes, the charge carriers would be ions, the cations and the anions. In a solution, for example, in a table salt solution, you'll have sodium plus ions and chloride ions that are free to move when electrodes are placed in these solutions. We do consider the conventional current as the flow of charge from a positive terminal to a negative terminal of a power supply. Just to explain these concepts using a simple circuit diagram. Here I've got a circuit that consists of a battery or a cell. The short line is the symbol for the negative terminal of the cell, and the longer line, the positive terminal. I've got a closed switch in the circuit. I've got a resistor in the circuit and an ammeter. Now, electron current. Electron current would flow from the negative terminal of the cell. The electrons will flow through the circuit, as I've drawn it here, clockwise through the circuit. Now, the electrons will only move if there is a source of electric potential energy, and that would be the battery or the cell. Conventional current, on the other hand, is considered as, by definition, the flow of charge from the positive terminal of the battery through the external circuit. And I'll symbolize it using an I. So here, a simple circuit consists of a source of electric potential energy, connecting wires which are considered as conductors with low resistors. An ammeter is used to measure the current strength in the circuit, and a resistor is a conductor that will make it more difficult for charge to flow through the circuit. And I want to continue with the definitions of simple concept. Electric current strength is the rate of flow of charge. These words could be changed into a mathematical equation that would look like this. I equals Q over delta T. It means the current strength is the rate, how fast the charge will move from one point to another point. From this equation, I'd like you to consider an equivalent unit to the ampere. 1 ampere is equivalent to 1 coulomb per second. Right? The next definition I'd like us to consider is that of electric potential difference. It is defined as the work done per unit charge. which we could also turn into an equation. V for potential difference is W for work per Coulomb charge. So the work done on a charge. It is also work done is related to energy transferred or energy used. And from this mathematical equation, which originates from the definition of electric potential difference, we get that 1 volt is 1 joule per coulomb. That's the equivalent unit to the volt. Next, I'd like us to look at the definition of EMF. EMF is the maximum amount of energy that a battery can supply, and you would be able to measure it if the switch in the circuit is open. And we use a voltmeter across the terminals of the battery. So a voltmeter across the terminals of the battery, when the switch is open, would measure the EMF of the battery. A voltmeter across the terminals of, or across a resistor, would measure the electric potential difference that the charges would have when they move through the battery. Here, where the charge enters the battery, if we consider electron flow, they've got a higher potential energy, a higher electric potential energy. By the time they have moved through the resistor, they would have a lower electric potential energy. So there is an electric potential difference between the ends of a conductor, especially resistors. When you have connecting wires, they have hardly any resistance. We can ignore the resistance of connecting wires. They have negligible resistance. Right, next I'd like to consider electrical resistance as a concept. It is the opposition that a conductor offers to the flow of charge. And with this, hand in hand with this, goes Ohm's law. Ohm's law gives you the relationship between the potential difference across the ends of a conductor and the current flowing through the conductor. That if the temperature is kept constant, will give us a direct proportional relationship. So if we would draw a graph of potential difference against current for a conductor of which the temperature is kept constant, we would get a linear graph. And they have discovered that the gradient of this graph is equal to the resistance of the resistor. So we can change this mathematical relationship into R equals V over I. If you want to write it as with the resistance as the subject of the formula. There are 4 things that affects the resistance in a conductor. And those 4 factors would be the temperature of the conductor, the thickness of the conductor, or some people would say the cross-sectional area, the length of the conductor. So the higher the temperature, the higher the resistance. The thicker the wire, the lower the resistance. The longer the wire, the higher the resistance, and then the type of material. Like copper has a much lower resistance than carbon or many other metals. Right, I hope this video, considering the simple, the basic concepts of involving electric currents helped you. Next, I'd like us to consider series and parallel circuits. See you on the other side of this video.